The goal today, or this time around, because we already had a goal for today, is to use the constant function rule, the power rule, the constant multiple rule, and the sums and difference rule. We're going to find derivative rules to find the point where tangent lines to the functions are horizontal. Okay, sounds like an ambitious goal. Let's get to it. Now, we're not going to use the first principles for this. I'm just going to tell you what the derivatives of these functions are. This first function here, so if y was equal to, so if this was y equals, let me go to black actually. If this was y equals 3x squared, then the dy dx would be equal to 6x. And I'm going to change this up a little bit. Instead of saying 2 over x, one of the things that you're going to find very useful when you are doing derivatives, if this is y equals this, is to sometimes change this to make it, when the denominator has a variable in it, is to make that into a numerator. So I'm going to call this 2 times x to the minus 1. Well, I'm hoping that makes sense, because x to the minus 1 means the same thing as 1 over x. So 1 over x times 2 will be 2 over x. So in that case, the dy dx would be equal to minus 2x to the minus 2. Okay, so I'm not using first principles or anything. I'm just simply telling you what they are. So those are the two derivatives. The first one was when y is 3x squared, the derivative was 6x. And when y was equal to 2 over x, which is the same thing as 2 times x to the minus 1, the derivative is minus 2x to the minus 2. Or I could put minus 2 over x squared, right? That's the same thing. That means exactly the same thing. So, is there a pattern? Some of you may have done this before, so you probably know what the pattern is. But is there a pattern between the 3x squared becoming 6x or the 2 to the x to the minus 1 becoming minus 2 to the x to the minus 2? Does anybody see what that pattern is? Can you go over how you got the second one again? Sure can, Ariana. Thanks for the question. So the first thing I did is I changed the 2 to the x, right? I changed this into 2 times x to the minus 1. Does that part make sense, by the way? That I changed it to make it look like that, Ariana? That the x to the minus 1. Remember, x to the minus 1 means 1 over x, all right? So that's another way of writing it. And all I'm saying is that I haven't told you, the sort of the secret to it yet, although I think Taj might have it there, is I just simply told you what the derivative is. The derivative of 2 times x to the minus 1 is minus 2x to the minus 2. I'm just telling you what it is, right? So I didn't go through a process to do it. I just told you what it was. Right? First principles that we've learned already would help us to do that. And all I did as well, Ariana, is instead of calling it minus 2x to the minus 2, I said leave the minus 2 on top and put the x to the minus 2 as x to the power of positive 2 on the bottom. Don't forget, don't try to remember that x to the minus 2 means the same thing as 1 over x squared. And that's why I can write it as minus 2 over x squared. Okay, does that kind of help a little bit? Okay, great. So is there a pattern? And Taj says you're just simply multiplying 2 times 3x. So what am I multiplying 2 times 3x? What's the pattern here, right? So you're right that I did 2 times 3x and got the 6x. But what else did I do apart from that? Are you subtracting the power by 1? Yes, Taj, that's exactly what I'm doing. So what you'll notice is that in the first case, I took the exponent, right? And I multiplied it by what was in front. So that's why I got 2 times 3, which is 6. Then I subtracted 1 from the exponent. So it just comes down to simply 6x. I did the same thing with the second one. All right, I multiplied the minus 1 times the 2, which gives me minus 2. Then I subtracted 1 from the exponent, so it's minus 2 times x to the minus 2. It is really that simple, Taj, and everybody else. That's the pattern. So you multiply the exponent by the coefficient, and you subtract 1 from the exponent. All right, so let's get to some rules of derivatives. Subtracting by power by 1, yes. So if you're looking at a constant, if its f of x is equal to just a number, where k is a constant, then f of x is just equal to 0, right? So the d dx of 8 is 0, right? And there's a very simple reason for that, okay? I'll show you what the reason is for that. In fact, let me go back to black actually. If I had a line which was supposed to be y equals, let's say, for instance, 8. So this was y plus 8 line. That's just a flat line, right? That's all that is, a flat line. What's the slope of a flat line? 0. So any flat line, which is what a constant would be, y equals any constant would be just a flat line. And what is the slope of a flat line? 0. So that's why d of dx of any constant is always going to be 0, regardless of what the constant is. Doesn't matter what the constant is, it's just going to end up being 0. It disappears, in a sense, right? So that's the first rule of derivatives. Second rule of derivatives is what you just saw me do a while ago. If f of x is equal to x to the power of n, as you can see there, where n is a real number, then the derivative function, f prime x, is n times x to the n minus 1. Exactly what you just saw me do. So d dx of x to the power of 5 is 5x4. See how simple that is? Right? It's taking that 5, multiplying it by the front of the function. So all that stuff we did in the first class when we were using first principles, that's important for us to be able to do, but this is the shortcut right here. And you're probably thinking, why did I show this in the first place? I know you're probably thinking that right now. Well, how about this one, d dx of 4x? Well, think of this as being 4 times x to the power of 1. X to the power of 1 means it's just simply x. We'll multiply that 1 by the 4, so that's going to be equal to 4. Then you're going to have x to the power of 0, which, by the way, is 1. So it's just 4. So d dx of 4x is just simply 4. Right? So if it's just a product of something with x, then you're just going to end up with the coefficient of the x. So d dx of 4x is equal to 4. Okay? So far, so good, hopefully. I mean, that's me saying I think it's okay so far, but I should check in. Thomas, how about you? Does that make sense, what I just did? Does that 4 make sense for this one? And does the 5x to the power of 4 make sense for the first one? Thomas, how about you? Are you there, Thomas? Where's Thomas? Where is Thomas? Thomas, there you go. You gotta let me know when you're there. Does that make sense, by the way, what I just did? That's the other question I was asking. Did the two derivatives I just got make sense to you, Thomas? The first one as 5x plus 4, and the second one of 4. Did you follow that? Could you go over it one more time? I sure can. All right, gotta stay with me, Thomas. It's important that you're paying attention the whole time. So let me go over it with you again. I'm going to take the exponent, which I'm pointing to right now, put that exponent in the front. So that's why the 5 has gone in the front. Then I'm going to take away 1 from the exponent. So that's the 5 came in the front, and the 5 minus 1 gives us the 4. The second one is 4x to the power of 1, right? I took the 4x and I put a 1 on it just to make sure that it kind of looked like an exponent. And what I'm saying is multiply that 1 by the 4, which is just going to be 4. Then take 1 from the exponent, so that's going to give us 0. And x to the power of 0 is just 1, so really all we're left with is just simply 4. Does that make sense now, Thomas? What I just did the second time, does that make sense now? Okay, good. Folks, you got to stay with us, right? It's important when I call out to you that you're right there responding right away and that you've been following along, right? I know that there are a lot of distractions in the room where you are. I understand that, but everybody's got to stick with me on this, all right? So those are the first two that we've done. That's the power rule. That's what's called a power rule, by the way. The constant multiple rule, excuse me. So if there is a number in front of the function, so for instance, minus 6, there's a minus 6 in front of that x cubed, then what you can do is you can find the derivative of the x cubed and then put the minus 6 at the end. Really, it's no different from what we just did a while ago. So if that's the function, hopefully nobody's going to be surprised at this. The answer to this would be minus 18x squared, right? So 3 times the minus 6, it's almost no different from what we did already, right? They call it constant multiple rule, but it's really just taking that 3 and multiplying it by the minus 6 and then dropping 1 from the exponent. There's your derivative. 18, so minus 18x squared. All right, so that's your dy dx right there. Okay. All right. Going to try a few more of those. Umair, how are we doing so far? Are we doing okay so far, Umair, with this? Okay, good. See, this gets a lot easier. Now, we're going to get some more complex derivatives. We'll get the product law and all of that stuff tomorrow, and quotient law and some more stuff, right? Or function of a function. There's all of that to come. But this is the most basic kind of derivative that we can get. Okay? Now, when it's a sum is easy, right? You just simply take the derivatives of each part and add them together. It's really that simple, right? So d dx of 5x cubed plus 8x squared is what you think it is. It would be first 15x squared plus 16x. That's all it is, right? So 3 times 5 is the 15, and then you drop 1 from the exponent to 2. 2 times 8 is 16. Drop 1 from the exponent, so it'll be 1. So there's your derivative. So the derivative of a sum is equal to the derivatives of each of the parts added together. Can we go over the last one again? Sarah says, thank you. No problem. As in the one I'm looking at right now or the one before on the previous page, Sarah? Which one are we talking about? The previous one? Sure. Okay, so all we're doing here is taking the 3, which is the exponent, multiplying it by the minus 6, which gives us minus 18, dropping 1 from the exponent, so we're now down to 2. So I get minus 18x squared. Does that? Okay. All right. And thanks for slowing me down, because I want you to if we need to. All right. So there we go. That's the next one. Hopefully everybody's okay with that. The difference rule is what you expect. Now, that allows me to bring in what happens if there's a square root. If there's a square root, I think it's useful for us to express that square root with an exponent. What's a good exponent to put for a square root of x? Right? Instead of saying the square root of x, what's a good exponent for the square root of x? Ashvan and Adam both say it's a half, and so does Stephen. Absolutely. So let's put that as a half. And then I'm going to say minus 5x. Instead of 5 over x squared, I'm just going to say x to the minus 2. So I'm trying to write these things. Thank you, Tamalea. Thank you, everybody who gave me those exponents of a half. I'm trying to write these things so they have exponents. Because when they have exponents, it's easier for me to come up with the derivative. So the first one had an exponent of a half, and the second one has an exponent of minus 2. And there's a minus sign in between them. So here comes my derivative. A half times 6, of course, is 3. So it's 3x to the power of, well, I have to take a 1 from that half. So I'm going to call this minus a half, right? So 1 minus a half is obviously minus a half. And then I'm going to multiply the minus 5 times the minus 2, which is plus 10x to the minus 3. All right, so I'm following the same principle as I did all along. Multiply the exponent by the coefficient, drop 1 from the exponent. Now, this can be rewritten, and I'm going to write it in Leibniz's notation now. So I'm going to write that dy dx, and I'm going to change things up a little bit. Instead of saying 3, and hopefully this is going to make sense to everybody, instead of saying 3x to the minus a half, I'm going to say 3 over the square root of x. I wonder if that sounds about right to everybody. Yes, Alexander, 3x to the to the, hope you have a minus in there. Is that a minus? I think you left off the minus though, Alexander. Remember, a half minus 1 will be minus a half. Make sense, Alexander? So that's one part that I think you might have left off of your answer. And then this second one I'm going to put as plus 10 over x cubed. Okay? Alexander, you see what I'm saying, by the way, that should have been a minus a half? Or hold on, let me see what you have there. You have 3 over x. Oh, I see what you're doing. I see what you're doing. You put 3 over x. But instead of saying, I got you now. Instead of saying x to the half, I'm putting it back as a square root. All right? So I get what you're saying now. I just realized what you're doing. Right. So 3 over the square root of x. So instead of saying x to the half, I'm putting the square root of x. And instead of saying 10 times x to the minus 3, I'm putting 10 over x to the power of 3. All right. Is everybody comfortable with what I just did? If you're not, then let me know. Taj, how about you? You're good with that? Taj is good. Okay, great, 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 great. All right. Okay, let's keep going. Now we're going to try to answer not just the derivative, but to use the derivative to do stuff with it. All right. Determine the equation of the tangent to the graph, which is exactly what your homework is all about, at x equals 1. The equation of the tangent to the graph of this thing, f of x equals all of that stuff there, at x equals 1. This might actually have been one of your homework questions. Can I go over it? Oh, okay. The question before this, Ariana, is that the one you're asking about? The one we just did? Okay, that's fine. That's fine. That's fair. Okay, so tell me what part. Is it from the very beginning or just at the very end? Just the ending. Okay, so this has to do with me writing the answer in a different format. So you see this answer here? Alexander actually had it right. He could write this as 3 over x to the positive a half, right? Because if I have a negative exponent, I can make that exponent become positive by putting it as a denominator. Or if it was negative as a denominator, I can put it at the top as a numerator, changing the sign. So when I change the sign, I also change whether it's a numerator or a denominator. Okay, right. And the same thing happens with the x to the minus 3. Instead of saying x to the minus 3, I put 10 over x to the power of positive 3. So that's where the second part came from. But the x to the half, of course, means the same thing as the square root of x. So hopefully that's okay. All right, it seems like you're okay with that now. I'll just put this again. So 10 over x to the power of 3. And thank you for that question, by the way. Keep those questions coming. Anytime I see that, that tells me that, first of all, people are courageous enough to step up when they're not sure. And secondly, it means that they're actually trying to follow along, right? The ones that really aren't doing what I've asked you to do is the ones that sit and just sort of stare into space and play with their Xbox when we're trying to get this done. That's not good enough, right? You got to stay with us and ask the questions when we're going through this. Okay, let's get to the next question. Determine the equation of the tangent to the graph at that point. Hopefully this is not one of the homework questions that I'm about to do for you, maybe, but we'll see. So the first thing we need is what? If I'm trying to find the equation of the tangent to the graph when x is equal to 1, the equation of a line, can anybody suggest the first step to getting that equation of the tangent? What would be the first step? The derivative. Thank you, Adam. So let's find, I just find it easy to use f prime x rather than dy dx, but they mean the same thing. So first term would be what? Right? What would be the first term of the derivative? So it's minus x cubed plus 3x squared minus 2. Give me the first. In fact, just give me the derivative. Somebody just put that in the chat, or you can unmute and tell us what you think it is. So Richard thinks it's minus 3x squared plus 6x. And I agree. If anybody needs me to do that a little bit more slowly, I can do that. That's fine. So Richard just gave me the first one, which is what I asked before. That's right. You're good. Why is it 6x? Okay. Multiply. Let's focus on that. I'm glad you asked. I'm glad you asked, Anika. Let's focus on this thing here for a bit. Let's multiply the exponent by the coefficient. What do you get when you do that? The coefficient times the exponent. What do you get when you do that, Anika? 6. Then take 1 from the exponent. So instead of it being x to the power of 2, it's going to be what? Isn't it just x at that point? X to the power of 1, if you like. Okay, good, 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 good. And you notice that the minus 2 kind of dropped off there. It's gone, disappeared. Poof, magic, gone. Remember what we said? Stephen is asking the question, just as I'm talking about it. What happened to the 2? All right? All right, did we just kill off the 2? Did we just sort of, okay, let's go back again and just remind you about something. The constant multiple, no, that's not it. That's not it. The constant function rule. When you find the derivative of a constant, a number, you know, just a 6 or a 10 or a million or whatever number it is, it goes poof, it's gone, right? It's gone to 0. So any constant that you have, there's no variable associated with it, it gets eliminated. All right, so that is what happened to our constant, that minus 2. All right, thank you for the question. So now we have our derivative function. This is the function that allows us to find the slope at any points. That's what this derivative function is all about. How do we use it? What do we now do with this if I'm trying to find the equation of the tangent when x is equal to 1? Help me out, folks. I'm stuck again. You know, Mr. Kamak just gets so confused when he's doing this stuff sometimes that he has to reach out to the class and say, help, help, help. I can't. I don't know what to do. So it's f prime of 1. Yeah, there you go. So let's just do that. Thank you. Thank you for rescuing me, Adam. So Adam says, because I don't know what I'm doing, Adam says find f prime of 1 in this function. So it's minus 3 times 1 squared plus 6 times 1. Okay, so let's do that. So that's just going to be minus 3 plus 6, which is 3. All right. Alexander, of course, is beating me to the punch every single time, right? Don't know how he does it, but he does. Anyway, so 3 is the slope of this tangent. But what else do I need? Because I'm not just trying to find the slope of the tangent. I want the equation of the tangent. I want the whole thing. I need to find the actual equation of this line, right? It's a line and it has an equation and it's a straight line. So it's y plus mx plus b. Find a point and use it in y plus. Okay, good. And what point would we put in then? What point do we have? What x and what y? Plug in a point, okay? Which point do you think is relevant in this case? Which point do you think? The 1. Good. We're going to put 1, not in the derivative function though. The 1 goes in the original function. There's the clue. There's the important things. I'm not sure if it's going to be 1, 3. Because Sarah, you might be thinking that the 3 that we just got represents a point. That 3 represents a slope. So what we need to do now is go back to the original function and find the f of 1, not the f prime, but the f of 1 in our starting function. So minus 1 cubed plus 3 times 1 squared minus 2. We got to go back to the original because the point that we're looking for is on the original line. So here we go. This is minus 1. This is plus 3. This is minus 2. Looks like this is 0, actually. Looks like this is 0. Oh, determining function might have maximum minimum. We're gonna leave that out. Let me bring that down. We're gonna get to that in a minute. So my math is saying that this is equal to 0. So the point that we're looking for, okay, Sarah, thank you, Sarah. The point that we're looking for is 1, 0. So the point that we're trying to find this tangent line is 1, 0. When you put 1 into the function, this 1 into the function, you get a 0 y value. Okay, so let's get to the y plus mx plus b. This is exactly what your homework is about, by the way, if I remember correctly. So 0 is equal to a slope. Okay, what's the slope again? I forget what the slope is. What slope are we supposed to be using again? Anybody remind what the slope? 3. Good. 3 times 1 plus b. So b is minus 3. So my equation, okay, let me try to bring this down some more. Let me extend the page a bit, bring this all down. All right, so the equation would be y equals, the slope is 3x. This is such bad writing. I'm ashamed of this. Let me try to tidy up my act a bit. 3x minus 3. Okay, the b is 3. The slope at that point, remember, when we put it into our derivative function was 3. So 3x minus, thanks, Alexander. I can't win in that race with Alexander. I just can't do it. Looks like he's always like 2 steps ahead of me. Anyway, so there's our equation. Now, here's another question that I'd like us to consider. 3x minus 3, that's our slope. Sorry, that's our equation of our tangent. All right, so let me put that beside it. Let's put that beside it here. Equation of tangent. This is the equation of the tangent. Okay, now determine where the above function may have local maxima or minima. I'm not sure how we're going to do that. Well, let me think about this for a second. The original function is a cubic function, minus x cubed plus 3x squared minus 2. So let's just, let me put a thing here. That function could potentially, since it's a negative lead coefficient, we know about end behavior, could potentially look something maybe like this, right? So it may have maxes and minima, right? So maybe there's a max here, sorry, a min there, maybe there's a max here. This thing that we're learning now about derivatives, is that supposed to help us to figure out where maxes and mins are? The answer to that question is actually yes. Can anybody think of a way that knowing the derivative could perhaps tell us where the max is? And we couldn't do this in advanced functions. When we're doing advanced functions, one of the limitations that we had was we could figure out where zeros were, right? You know, we could set an equation equal to 0, and we could factor it, and we could use zero product law. We could figure out where the zeros were. We had the basic idea of the shape of the function. But I think this new tool, okay, let's see what Stephen is saying now. He's saying the derivative at max and min would be equal to 0. He's right. Why is it equal to 0, Stephen? Or anybody else? He's right, by the way. Why should the derivative be 0, equal to 0 at a max or a min? Is there a reason for that? Zero slope. If you think about it, any line that is a tangent at a max or a min has a 0 slope. It's a flat line, right? No, not just because it's linear. All these tangent lines are linear, but the slope of a horizontal line, which in fact we talked about that a few minutes ago, is 0. So if we can find where the derivative is 0, we now potentially know where the max or the min of the function is. Later on, we'll talk about which one is a max and which one is a min, but that's why this could help us out. So let's see if we can use that in this case. Remember what the derivative was, right? The derivative, where's my derivative? Here's my derivative, minus 3x squared plus 6x. That's what we said the derivative is. So I'm going to write that derivative down again. So minus 3x squared plus 6x. So we're trying to answer this question now. So the derivative, keep using different colors here, minus 3x squared plus 6x. Did I write that down right? Hang on. Yeah, minus 3, okay. So the question is, where is this equal to 0? Well, why don't we just set it equal to 0? So minus 3x squared plus 6x equals 0. And we can solve this, can't we? How do we actually solve this, by the way? How do we solve this quadratic equal to 0? What's the strategy there? I'm setting it equal to 0, but I need to know how that helps me to, how do I solve where this is equal to 0? We factor, okay? What is the factor? What is it to find the zeros? Yes, good. So what are the factors of, or what is the factor of, the common factor of what we're looking at here? What would be a good common factor for us to use for this? All right, we're trying to solve this. What's a good common factor? I'm going to use the minus 3x. I'm going to go with Cush's version. Adam, you're not wrong. You could have used a 3x, but I think it's more convenient for us to use the minus 3x. So minus 3x, which would give us x minus 6 equals 0. And you can confirm for yourself that that common factor does work. If I'd used a positive 3x like what Adam said, then I'd have had a minus x, then a plus 6. Okay, but that works just as well. So here are my zeros. Okay, what is this minus 2 here? Yes, 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 absolutely. It's not minus 6 at all. Thank you, folks. And again, I'm not doing this on purpose. I promise you I'm not doing this on purpose. Okay. So that is in fact minus 2. Yes, absolutely. X minus 2, not 6. Yes, Alexander. Thank you. Thank you, Ashfan. Okay. Thank you to all of you who wouldn't allow me to trip myself up like that. Okay, good. So what are the zeros here? There are zeros at, where are the zeros here, folks? Where are the zeros of this function? What are the values of x that are going to get us 0 here? Anybody? I'm not asking anybody in particular, just asking 0 and 2. Good. So turns out that this function does have local max or min at 0 and 2. As to which one is a max, which one is a min, we can probably guess because this function is a function that goes from quadrant 2 to quadrant 4 based on its end behavior. So the first one that we got, well, there's a 0 and there's a 2. I'd say the first one probably a min and the next one is probably a max. But for right now, we're not going to get into how to differentiate between maxes and mins. It's just asking for local max and min. So we're just going to assume that one is a max and one is a min. Okay? Determine the location of the x-intercepts and graph the function showing all intercepts and turning points. I'm going to leave that for now because I want us to get through all the questions that we have, but that is it. That is perfectly doable, something that we could do, right? We could find all the x-intercepts of that by factoring it and so on and so forth, and then we could draw it. But let's just keep going with the derivative stuff, the calculus stuff. All right, this is a more challenging question. But what I've found is that my class is more than equal to the task. Let's read this through and see if we can make some head or tail of it. Find a point or points, in other words, there could be more than one, on the graph of f of x equals minus 4x cubed, where the tangent line at this point is perpendicular, so the normal, we talked about the normal before, to the line y equals 1 over 48x minus 3. Read that to yourself. I'm going to stop and pause for a minute. Ask you to read that to yourself again. I can make this a little bigger for you. Actually, the only way to do that is to zoom in some. I want you to read that and start thinking of a strategy that we could possibly use to figure that out. It sounds like it could be more than 1.2, right? Where the tangent line at this point is perpendicular to the line 1 over 48x minus 3. All right. The points on the graph where the tangent line, so the tangent line is perpendicular to that line. Now, 4x cubed, just for the record, and I'll draw a quick little thing here. Probably look, is it a minus or a plus? Minus, okay. So minus 4x cubed probably looks something, yeah, I'm going to mess this up. I know I'm going to mess this up. It's the opposite of that. So it probably looks something, okay. Probably looks something like this. Kind of, sort of, okay? If you drew this on Desmos, I'm sure it wouldn't look quite like that, but it's kind of something like that, right? So the question is saying, where the tangent line on this function is perpendicular to this other line, 1 over 48x minus 3, right? So 1 over 48x minus 3 is going to be a line that, minus 3 is somewhere down here. All right? And has a slope of 1 over 48. So it's a fairly flat line. Let me see if I can do a fairly good job of that. I'll put that in a different color. So it's a fairly flat line like that. Okay. So no, we're not asking, let me just be clear. We're not asking for where this line intersects with the function. That's a different kind of question. we're saying, let me go back and show you, where the tangent line at this point is perpendicular to the normal of this. So the normal of this line is a line that is going to be at right angles to this line right here. All right, so it's going to be at right angles. So let me go back and show you again. The point on the graph of the minus 4x cubed, where the tangent line at this point is perpendicular to the normal of the other line. Okay, so where is a good place? And it might be more than one point, by the way, right? Where is a good place for us to start with this? What do you think is a good place for us to start with this, folks? Anybody? What would be a good starting point? Nobody has an idea of where we're going to start. I mean, what have we been doing for the past couple of minutes, right? Unless we're not clear on the question. Okay, find a derivative. Okay, find a derivative of the normal. Of the normal. Interesting. Sarah says. Not sure about the derivative of the normal. There's something we have to do with the normal, but I don't think it's a derivative of the normal, though. I think we do have to find a derivative of the 4x, the minus 4x cubed. So why don't we start with that? So the f prime, let me go back to black, actually. Can anybody tell me what that derivative is, by the way, of the function? What is that derivative? So let me see, minus 12x squared, good. Okay, so that's good. Are we, everybody, so are we more comfortable with finding these derivatives at this point? Everybody okay with that derivative? That makes sense? Okay, good, good, good. Now, the tangent line at this point is perpendicular to the normal to the line. So we need to figure out something to do with this y equals 1 over 48 x minus 3. The inverse of the normal would be the derivative, Stephen is saying, I think. Okay. What is the slope of the tangent line that we're looking for, though? What is the slope of the tangent line that we're looking for? Does anybody know the slope of the tangent line that we're looking for? Minus 48. Is everybody in agreement with that? Let me write that down. So the perpendicular to the line, the slope to the perpendicular line would be equal to minus 48. I just want to make sure that, can you explain how? Okay. All right. Remember the negative reciprocal, Kushi? Remember that negative reciprocal that we did a few minutes ago? Okay. So this is the line that we're trying to make it perpendicular to. It's perpendicular. The perpendicular just means normal to this line, and this line has a slope of 1 over 48. Of course, the 1 over 48 represents the slope of the line. You know, y equals mx plus b. Remember that part? Remember that stuff from grade 9? Yeah? Okay. So what we're doing now is we're saying, why don't we take that and flip it over, okay, and figure out what the negative of that number is. Does that make sense? So we ignore the constant here too. Oh, yes. Oh, yes, absolutely. Well, no, we're not trying to find a derivative though, Kushi. What we're trying to do is find the slope of the line that's perpendicular to this line, right? So it has nothing to do with derivatives right now. What we're doing, we're going back to y equals mx plus b is what we're doing, right? So do you get the derivative equal? Yeah, we're going to get to that in a second, Tash. But let's just make sure that Kushi understands that the constant here is just the y-intercept of the line. That's all that is. Okay? So really all we're trying to do now is we're trying to figure out what the slope of this perpendicular line is. Remember, the tangent line that we're looking for is perpendicular to this line, which has a slope of 1 over 48, and the negative reciprocal to that is equal to minus 48. So does that make sense so far? Okay, good. So now we need our slope to be equal to this minus 48, right? And our derivative, we said, was minus 12x squared. So shouldn't we therefore take the minus 12x squared and set that equal to the minus 48? Shouldn't that kind of sort of make sense? Because we're trying to figure out where the points are on the line that have this slope of minus 48. Remember, this minus 12x squared is a slope equation. This gives us slope, right? And we're trying to figure out where on this line has a slope of minus 48. So we're going to set them equal to each other. Does that hopefully make sense? I want to just check in with the room on that. Is everybody following that so far? Don't forget that our derivative function is a slope calculation tool. And we want to find where the slope of this function is equal to the perpendicular of this other line, this normal line, which is 1 over 48. So the perpendicular to that is equal to minus 48. Does that kind of sort of make sense? I need to get a little feedback from the room here. Setting them equal to each other, does that make sense? Ashwin says yes. Okay, good. Okay, fine. So we need to solve this now. We need to solve this. So of course, you're going to divide both sides by the minus 12. So x squared is equal to positive 4. And obviously, we take the square root. So x is equal to the square root of 4. But every square root has a plus and a minus. So it's plus and minus 2. So we now know that these are the 2 points at which this graph of minus 4x cubed is going to have a slope which is the reciprocal, the normal to the 1 over 48 line, okay? And that occurs at 2 spots when x is plus 2 and when x is minus 2. So there are, in fact, 2 points, and that's what the question was kind of suggesting, right? So these are your x values, but really what we need to get are coordinates, right? I need an x and a y coordinate. So these are my x coordinates, plus and minus 2. How do I find my y coordinates? Can you help me out with that, please? What are my y coordinates? How do I find my y's? Where do I go? Where do I put this plus and minus 2 to find my y coordinates? Where does that belong? Do I put that in the original function, or do I put that in the derivative? Where do you think it makes sense to put the plus and the minus 2? One at a time. We put the 2 first, and then we put the minus 2. Where do you think that should go? I'm trying to find the points on the original function. Well, that's kind of a clue. That's kind of giving it away. I'm going to put that plus and minus 2 back into this function up here, right? Remember, we're trying to find the points on this graph. And we now know where in the function, yes, the original function. So we're going to figure out that by putting the 2 and the minus 2 back into this original function. So I'm going to find the f of 2 and the f of minus 2 of the original function. So the f of 2 gives us minus 4 times 2 cubed, which is equal to 8 for minus 32. And f of minus 2 is minus 4 times minus 8 times minus, so positive 32. So the 2 points where this happens are 2 minus 32 and minus 2, 32. The function itself. Okay, hopefully I didn't go too fast on that one. So those are the 2 points at which the normal is going to hit the function. Okay, the normal to the other line is going to hit the function. Okay, I think we have one last question, and then I'm going to give you a lot of time to work on the homework. I believe this is, let me just double check. I think this is the last question we're going to be doing. Oh, yeah, I'm going to leave that. Yeah, I'm going to leave that last one. I'm not going to do that last question. Yeah, we're just going to do this and say, oh, actually, since we have some time, I can actually go back and look at the question. I think it was Ariane. I have to go way back in the chat to figure out who it was. Wanted to ask for some help with one of the questions from the homework, and I'm quite happy to do that. But let's just finish this up first. So, subway train travels from one station to the next in 2 minutes. Its distance in kilometers from the first station after t-minutes, and they give you a function. At what times will the train have a velocity of 0.5 kilometers per minute? Now, let me remind you that this, and we did this when we were doing rate of change in the first unit. This function is a distance function, right? It tells you how far you are from a particular point. I think it's out from the first station. Okay, so this is the distance from the first station. Excuse me a minute. So this is the distance from the first station. This is not a velocity equation. But we did say that if you take a distance equation and use the IROC at a particular point, that IROC represented the velocity. So now we can actually come up with a derivative function, which would be your velocity function, if you think about it. So this, therefore, would suggest that what I want is an S prime of t function, which is going to give me velocity at various points. So what I want from one of you now, no wheel today, I'm giving the wheel a break. One of you needs to give me what that derivative is of this function that I just circled a few minutes ago. I'm getting 2t minus t squared. Is he right? Is Richard right? What do other people think? Right? I don't want to 2t minus t. Okay, I have a different. Okay, Danny gives me something else here, right? So, oh, I see. You left out the 2. Okay, good. You put it. You put the answer in before you were ready to put it in. I got you. Okay, that's all right. Ashvan is 2t. So everybody seems to be on this 2t minus t squared trip here. Okay, so let's confirm that. Yeah, the derivative of this function is 2t minus 3 times 1/3 is 1. So that's just going to be t squared. 2t minus t squared. Absolutely. Thank you, Ashvan. Thank you, Stephen, and Danny, and Richard. Okay, good. So what am I going to do with this now? Do I set this equal to 0.5 or do I put 0.5 into the function? I'm not sure what to do, right? I want to figure out when the train has a velocity of 0.5 kilometers per minute. What do I set this equal to 0.5 or do I put 0.5 into the function? What Stephen says equal to 0.5 and Richard is on the same page with him. What do other people think? Are these guys equal to? Okay, Cushy, Richard, and Stephen all seem to be singing from the same hymn sheet. Equal. Okay, all right. Okay, you've convinced me. You've convinced me. So 2t minus t squared is equal to 0.5 because we're saying the velocity is 0.5, right? So we're going to set it equal to 0.5. Absolutely. All right. But how do we solve this? Okay, that's all well and good. How am I going to solve this? Can anybody help me out with that? Do I need some sort of a quadratic formula or something? What am I going to do with this? Factor? Well, before we factor, not quite yet. It has to be. I look at what Sarah just said. Sarah said, "Well, set it equal to 0," and she's right. It's factoring is not going to help you if it's not equal to 0 because factoring, right, is dependent on the zero product law, which says if I'm multiplying two things and I'm getting 0, then one of them has to be 0. So we have to set this equal to 0 first. So I'm going to go with 2t minus t squared minus 0.5 is equal to 0. I agree with you, Sarah, on that. I absolutely agree with you on that. No, you're probably thinking, that doesn't look like something I can factor. What am I supposed to do with this thing? Well, let's do a little a little trick on this. Let's first of all put the minus t squared first. It looks more like a quadratic that we're used to. So minus t squared plus 2t minus 0.5 is equal to 0. So it kind of looks a little bit more like what we're used to, right? I would think. But I'm still not quite sure how to factor this. Any suggestions on some things that we can do to make this a little easier on ourselves? Anybody? Anybody out there? Quadratic equation? We could do that, but I want to see if there is some way I can avoid using a quadratic. Yes, you can use quadratic equation. Let me just agree with you on that. You can use this as a quadratic equation. Yes, true, because you have an A, a B, and a C. But before we get there, okay, let's see what Stephen is saying now. Half t squared. So you're factoring out the half. That's interesting. That's very interesting. How about if we did this though, Stephen? And it's kind of on the same plane as you. How about if we multiply through everything by, let's do this first. I don't factor, yes, I like factoring out the negative, but here's how I'm going to say it. How about if I, remember, this is equal to 0, right? How about if I multiply both sides of the equation by minus 1? So this side by a minus 1 and this side by a minus 1. I don't want it to seem as if I'm minusing 1 from this. I want to multiply by minus 1. So let me make that more obvious. Let me put the minus 1 in the front and then the 0 behind it. Well, clearly the right-hand side is still going to be 0 because multiplying 0 by anything is still 0. But the beauty of what we've just done is kind of the same thing like what Alexander is suggesting, factoring out the minus 1. That's kind of the same thing here. Multiplying by minus 1 makes this become positive t squared minus 2t plus 0.5. And the other thing that I think is useful for us, rather than using quadratic formula, is multiplying now both sides of the equation by 2. So again, the right-hand side stays as 0, which is useful, but the left-hand side becomes 2t squared minus 4t plus 1. Why did I do that? Because I think it would be easier. Yeah, you factor negative. That's fine. It's kind of on the same track as I said, Alexander. Because I find it easier that maybe I can possibly factor this, and we'll try this out in a minute, without using a quadratic formula. Maybe I can possibly factor this without having to use a quadratic formula. Multiplying by 2 clears away this half right here, right? 2 times a half obviously is 1. Could we multiply? Yes, Richard. Yes, 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 absolutely. If you multiply through by minus 2, it's the same thing as doing this in 2 steps. I did it in 2 steps by multiplying by minus 1 and then multiplying by 2. But yes, Richard is right. Multiplying by minus 2 does it in 1 step. We get the same result by doing that. Now, the question is, can this be factored? Well, let's try my Magic X method that I mentioned to you the class the other day. You don't have to use the Magic X if you don't like it, folks. Don't use it if you don't like it, right? The top is 2 and the bottom is minus 4. Are there two numbers that I could, actually looks like you can't factor it. I'm just trying to think now, can I factor this? Maybe I can't because the product is 2 and the sum is minus 4. And I can't think of two numbers, 2 and 1. No, looks like we are stuck with the quadratic formula after all. So you know what this means? Is I can't think of any way to factor this. It means that, unless anybody else can, I can't think of a way to factor this. It means that from the very beginning, we could have used a quadratic formula. So let me go back and give credit to somebody who brought the quadratic formula up in the first place. Let's see, that was Sarah. I thought that once we did this, and I, probably did this question before, but don't remember whether we could have factored it or not. We could have used a quadratic formula all along, right? Because I thought that doing that would have made it factorable, but it doesn't look like it is. So from this point here, where are we at now? Where are we at? Where are we at? Where are we at? Here we go. From this point here, when we had this, we could have just simply used minus 1, 2, and minus 0.5, 0.5, and put that into the quadratic formula. If we keep it as that, it factors. Really? Tell me about that, Alexander. I'd love to hear about that. Factors into what? you give me the factors that you came up with, because I'd be very curious about that. What factors? T into t minus 2. Okay, what you're talking about is up here, factoring up here. That's what you're talking from, factoring from this line right here. That's the line you're talking about. Yeah, the problem with that though, Alexander, is that it has to be equal to 0. So if you're leaving the 0.5 on this side, then factoring it like that doesn't really help you, right? Yes, you can factor this line, but you set it equal to 0.5. You can't solve that. You see what I'm saying, Alexander? I want to make sure. Oh, you put the 0.5 on the left, but then you're only factoring out the first part of it. But how does that help you to solve it, though? I'm not sure I can. Maybe you could tell us, because I'm open to learning from you, right? Factoring just one part like that. Okay, all right. So, folks, looks like we're stuck with a quadratic formula. Didn't realize that we were, but it looks like we are. So let me go to that very quickly. And I remind you what the quadratic formula says. It's minus b plus minus the square root of b squared minus 4ac all over 2a. Okay, so let's see where we are with this now. That would be minus 4, minus 4, which is 4, plus minus the square root of b squared would be minus 4 squared minus 4 times 2 times 1 all over 2 times 2. Okay, did I do everything right there? Let me double check that. So let's see now, minus 4 squared minus 4 times a times, yeah, that looks about right. So that's 4 plus and minus the square root of, looks like 16 minus 8 to me, which is 8 over 4. Okay. And if I ask for this in exact form, so that's 4 plus and minus that, that's equal to 4 plus and minus the square root of, oh, sorry, 4 plus and minus the square root of, that's 4 times, so that's 2 root 2 over 4. So we should have, reducing that down, 1 plus a half of root 2 plus and minus. Only one of these I think is going to work. I think only the 1 plus is going to work. So it looks like there's only one time, because one of these times is going to be negative. And obviously negatives wouldn't make sense for this, because we're trying to figure out at what times. Looks like it might only be 1. Or do both of these work out to be positive? I'm not sure. Half of root 2, does that work out to be a positive? I'm going to grab my calculator here. Let's see, 1 minus, so 4, hope everybody's doing this with me, 2 square root of 8 over 4. Oh, looks like we do get 2 answers. So you can tell me if you're getting the same thing I'm getting. I'm getting an answer of 0.29, or approximately 0.29. And the other answer that I'm getting is 1.7. Okay, can I just, okay, yeah, I think that's what I'm getting. Everybody is getting the same thing? Yeah, okay, good. All right, so I actually thought that this was going to work out a little nicer, but it's not. Anyway, so let me put the answer. Let me put a therefore statement. Therefore, the train, is it a train? The train will have that velocity of 0.5 kilometers per minute at 0.29, at about about. It's not exactly, not exact. 0.29, 0.29. Is this minutes? Is this minutes? Yeah, minutes. Minutes. And 1.7 minutes. Okay. Are we all on the same page with this? All right. So we have loads of time left. Well, a bit of